सीताराम सर भल अच्छा तो
हाँ सर गुड आफ्टरनून।
गुड आफ्टरनून सर आ कौन खबर
हाँ भल अच्छी सब भल चलची
मु देखली मु देखली केही नाहंती सेति भाई आपन संगे टिके गप्पा शुरू करले
हाँ 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 इट्स गुड नो प्रॉब्लम सर। आ भल स्पीकर रखछन्ती अधिका लोक हो जिवे।
ए यूट्यूब लिंक ता आपन पाइछन्ती कि नहीं
हाँ हाँ यूट्यूब टा अच्छी है।
हाँ यूट्यूब रे हमें ब्रॉडकास्ट कर दउछु संगे
हाँ
संगे
संगे संगे सेटा बेटर माने अधिका
ସେଇଟା
लोक।
ଆମେ ହଁ କାଇଁ ଆମେ ଦେଖିଲୁ କଣ ଗୋଟେ ମାସ ପାଇଁ ସବସ୍କ୍ରାଇବ କରିକି ଲାଭ ନାହିଁ କାଇଁ ଆମର ପୁଣି ଅଗଷ୍ଟରେ ପ୍ରଫେସର ଶ୍ରୀପତି ପାନି ଏଣ୍ଡାମେଣ୍ଟ ଲେକ୍ଚର ଅଛି
हाँ हाँ हाँ
ବୋଲେ ଆମେ ଦେଖିଲୁ ସେଟା ଟୁ ବେଟର ହବ ଏ ୟୁଟ୍ୟୁବ ବ୍ରଡକାଷ୍ଟିଂ
हाँ हाँ यूट्यूब बेटर बेटर यूट्यूब नो प्रॉब्लम।
ହଁ ସେଥିପାଇଁ ଆମେ ଡିସାଇଡ କଲୁ ଥାଉ ଆଉ ଗୁଗୁଲ ମିଟ ଯେମିତି ଚାଲୁଛି ଚାଲିଥାଉ
हाँ गूगल मीट क्लियर हो सब अच्छा। हाँ अपना क्लास सब ऑनलाइन चलची।
हाँ सर क्लास ऑनलाइन ଚାଲିଛି
ଆଜ୍ଞା
କ୍ଲାस ऑनलाइन ଚାଲିଛି सर
ଆଜ୍ଞା ଆଜ୍ଞା। ଆଉ ସାର୍ ଆସିଛନ୍ତି ଜିବି ବେହେରା ତ
ସାର୍ ଜଏନ୍ କରିନାହାନ୍ତି କରିବେ
ସାର୍ କରିବେ ନା ଏଠି ଜିବି ବେହେରା।
ହଁ ହଁ
ହଁ ହଁ
हेलो हेलो हेलो
हाँ ऑडिबल।
हाँ ऑडिबल ना
हाँ
ओके थैंक यू
सर फुल स्क्रीन दादा फुल स्क्रीन कर दियो।
क्या बोलो
ये पावर पॉइंट का दे दियो।
ऑन कीजिए ऑन तो नहीं ऑन कीजिए
चला आसुची करा खुला हटे एटा खुले पेंटिंग देंगे
टॉप प्रेजेंटिंग लेकिन और
आई रो फुल स्क्रीन कर
फुल स्क्रीन करो तुम्हारे तो ऐसे
मैं जान नहीं हमारा दिसला काय
हाँ हाँ ठीक अच्छी ठीक अच्छी ठीक अच्छी परफेक्ट।
मैं लोन दे दो उसका कमाई रखा इसी का शॉर्ट हो
काम करने को बाबू दे जो मन को खिला दे
सर नमस्कार अनादि सर नमस्कार
Hello, Vijay.
सर
Can you hear me?
सर पलोज सर बुला रहे थे
अच्छा अच्छा
Thank you for calling me at least.
Sir.
Ajay actually gave me the link.
Sir. Sir.
Amaresh, how are you, Amaresh? Has he joined?
हाँ सर नमस्कार ଭଲ ଅଛି ସାର୍
Nice to meet you people.
ହଁ ସାର୍ ଭଲ ଅଛନ୍ତି
Yeah, very good.
अमरेश बिसिंग को टाइम रिमाइंड कर दबा होता है
Good afternoon, Professor Maitra.
Good afternoon. How are you?
Good, good. How are you, sir?
I'm good too.
Okay. Professor Behera has also joined. Professor G.B. Behera has also joined the platform.
Okay.
So, good afternoon, Professor Maitra.
Good
I am
afternoon.
Professor Mishra.
Very good afternoon.
Good afternoon, Professor Maitra.
Sir, namaskar, sir.
Namaskar. Namaskar, everyone. Professor Behera, I haven't met you perhaps before, but I'm indeed very delighted and honored to meet you on this occasion.
Dr. Mishra?
Sir, this is just.
Hello.
Okay, sir.
Yeah, good afternoon to all of you.
Yes, sir. So we'll start, sir.
Yeah, you can start, please. You can start.
Yeah, we can start at 3 o'clock. Just 1 minute, sir.
Yes, Dr. Saab, you can start.
Okay. So, good afternoon, everybody. As you know, today we have Professor G. Behera Endowment lecture. So, in that occasion, as the head of department, I myself, Comrade Mishra. So, I will introduce the university and the department in short. So, it is our privilege that we have amongst us today our Honorable Vice Chancellor Professor Sanjeev Maitra, a GBS, former professor and founding member of the School of Chemistry, Professor G.B. Behera, President Chemistry Seminar, Professor A.K. Behera, distinguished speaker of today's endowment lecture, Professor Uday Maitra, Department of Organic Chemistry, IIC Bangalore, dear colleagues, students, ladies and gentlemen. It gives me an immense pleasure to extend a very warm welcome to you all on the occasion of third Professor G. Behera Endowment Lecture, organizing by School of Chemistry, Bangalore University. I also welcome all the honored guests present here today. I would also like to express our gratitude to our esteemed speaker, Professor Uday Maitra, Department of Organic Chemistry, IIT Bangalore, who has accepted our invitation to deliver the seminar. Bangalore University, established in 1967 at Sambalpur and started its journey at the Behera campus since 1973. It occupies an important position in the academic scenario of the state of Odisha and India. The School of Chemistry, a pioneer department in teaching and research in chemistry in Sambalpur, started functioning in the Behera campus from 1973. The school has enriched with the funding of around 2.5 crores funded by DST and AGC under FEAST and DRS program, and is boosted up with a group of highly qualified and dedicated support personnel. The school has carried out almost 20 major research projects of around 5 crore funded by various agencies like DHD, EDC, CSIR, DRNS, and so on. The faculties are working in diverse fields of research, which includes surface chemistry, supramolecular chemistry, photochemistry, biophysical chemistry, organic electronics, organic synthesis, nanomaterials and composites, organometallics. The school has also undertaken collaborative research work with the international reputed universities, industries, and research laboratories, and publishing research papers in various peer-reviewed journals. Every year, a large number of students qualify NET GATE and pursuing their higher studies in various reputed institutions around India. I would also like to refer here that the Professor G. Endowment lecture was instituted by the MSc 1975 batch in the Golden Jubilee year 2020. The first lecture was delivered by Professor K.V.R. Chari, Director ISR, Behera, and the second lecture was delivered by Professor Santanu Bhattacharya, Director ISCS Calcutta. This time, we are proud to have an eminent personal like Professor Uday Maitra, who agreed to deliver the lecture to enlighten us with the knowledge of science. So I sincerely hope you will enjoy today's talk, and thank you all for your participation. Now, I would also like to welcome and request Professor Uday Maitra, who is the retired professor of this department and one of the alumni of the MSc 75 batch, to say a few words about Professor G. Behera and the endowment lecture. Sir.
Yeah. I have to address now?
Yeah. So,
Okay.
yeah. Thanks, Amaresh. And my respect to, my regards to Professor Behera, my teacher, Professor Moulik, Professor Anandi sir, Professor Uday Maitra, and Vice Chancellor Professor Mittal, my friends. To say about my teacher, Professor G. Behera, let me start with, during the Golden Jubilee celebration of the department, the alumni of our batch in 1975 batch decided to contribute something for the benefit of our alma mater. Unanimously, it was decided to institute an endowment lecture series in the name of our teacher, Professor G. B. Behera. Dr. Ramkrishna Mishra from Northwestern University and Dr. Somprakash Sahu from New Jersey immediately contributed 1 lakh rupees each for organization of the endowment lecture series. It says about the respect and recognition to a great teacher like Professor Behera. To say something about him, he was born in 1939, received MSc and PhD degree from Ravenshaw College, and joined this university in 1969 at the time of the inception of this department of chemistry. He took the lead role to develop the department to its present form. He has visited the United States as a UC visiting scientist. His able leadership generated momentum to create a vibrant research environment in addition to teaching activities in the department. His research interest include organic synthesis, surface chemistry, and reaction mechanism. He has also done some work in natural products. He has published more than 150 research articles and reviews in various reputed journals. Because of his enormous contribution, the School of Chemistry at Bangalore University could make its mark in Indian academia. As a teacher, he is par excellence, and as a recognition, he has been awarded Professor B.S.R. Gupta Award as the best teacher in the state of Odisha. He has been awarded Professor B.N. Ghosh Memorial Award from I. To say something about his remarkable contribution. Some of his remarkable contributions in Professor Behera's research work are: at the age of 34, he published an article in JOC from Sambalpur University Lab, and that too on a general work with the title Protection of Thiazers. On the month of retirement in 1999, he submitted the review article in Chemical Review, which was published in 2000, and till date, it has 1650 citations. He established an atomic or group descriptor, HD, steric density, for correlation analysis in chemical reactions. It is the van der Waals volume by the mass of the group. This work has been reported in Physical Organic Chemistry book by Roger Gallo. For the first time, he reported a hydrophobic force field in micellar system in Mysore system how this hard force works. During his tenure as head of the department, he introduced advanced quantum chemistry as an elective course in MSc for the first time almost in Indian universities, and surface chemistry in MPhil, where he prescribed PhD thesis as the text materials. After his retirement, he engaged himself in developing the academic scenario in his area and more specifically in Kalandi district. He is the nicest person I have ever encountered. My regards to sir and thank you all.
Thank you, sir. Now, I would like to introduce to you our Reverend Vice Chancellor, Professor Sanjay Mittal. Professor Mittal is a true academician. He was awarded with gold medal in both graduation and post-graduation. He has 40 years of post-graduation teaching in the branch of business management, research, and administrative experiences. He started his career in 1980 from the Department of Business Management, MD University, Rohtak. Afterwards, he joined to Rukmini Devi Institute of Advanced Studies, Delhi, and subsequently at University School of Management Studies, Guru Gobind Singh Indraprasth University, Delhi. During his tenure at Guru Gobind Singh University, he held many key administrative positions such as Dean, University School of Management Studies, Coordinator of Entrepreneurship Development Cell of the University School of Management Studies, Director of Academic Affairs at Guru Gobind Singh Indraprasth University. Before joining Soundpo University as Vice Chancellor, he was the Director of Academic Affairs at Guru Gobind Singh Indraprasth University and Professor, University of School of Management Studies. He has successfully supervised 11 PhD scholars and 4 more scholars are in the pipeline. He has published more than 120 research articles to his credit in peer-reviewed journals. His area of interest is marketing, international business, and entrepreneurship. He has visited many countries like US, Europe, South Africa, Denmark, Sweden, Singapore, Dubai, etc. He is also an esteemed member of the National Board of Accreditation and National Assessment and Accreditation Council. He has joined as Vice Chancellor of Sambalpur University on 25th January 2021 with a vision and strong determination of transforming this university to a greater height. He is proficiently guiding all the stakeholders of the university to upgrade the rank of the university to the next level. With this few words, I would now like to welcome Professor Mittal to say a few words.
And thank you very much. So thank you very much, Doctor. And good afternoon to all of you. So chemistry is such a field. I think I am not having much of the knowledge about this particular field. And but in any case, I am quite happy that my department of chemistry is organizing this seminar. And I think it is a series of seminars they are trying to do it. And I think a few days before also they have done a seminar relating to some Nobel Prizes, which have been there. And now this is another seminar that they have started. And my congratulations to you. And I am really delighted that very renowned galaxy of experts have been there in this seminar. And they are going to basically give a lot of knowledge and information sharing to all the participants who are here to attend this type of a seminar. I personally believe that such seminars are of great importance just because of the reason that whatever has been the latest developments in the respective field, I think those developments can be showcased and highlighted by the experts who are already involved in doing research and consultancy in their own area. Chemistry is a very vibrant field, friends, and I personally feel is that our whole body is full of chemistry, and for that particular reason, I think a lot of innovations, a lot of inventions, and a lot of research is being done. I was listening to the resource person, and he has also highlighted that there are a lot of laurels that have been there with the Department of Chemistry, Sambalpur University. And I think whatever legacy that we are having, we should maintain that legacy. And in future also, this Department of Chemistry has to do some great work. And I'm quite happy that Department of Chemistry is trying to have a lot of funded projects also from different funding agencies. And they are also in a position to create an extension counter and extension block of the existing department. And these are all welcome steps. And as university also, we basically are looking forward how exactly we can improve the H-index of the university. I think chemistry is contributing a a lot in this particular direction. And as rightly said by the HOD chemistry, as a university, we are trying to look forward how exactly we can improve our ranking in the NAC. And as a result of that, I think all these seminars, these activities that we do, they are very, very helpful. And I congratulate the HOD and his team for organizing this wonderful seminar by inviting a lot of distinguished and intelligent resource persons and all the participants across the country, and hope that whatever deliberations are going to be there as a part of this seminar are definitely going to basically add not only to the pool of knowledge, but will also help to update the knowledge bank of all the participants who are going to attend this seminar. So with these few words, my congratulations and my best wishes for this seminar which you are organizing. And I'm really thankful to all the resource persons who really have come over here to deliver their expertise and their talk for the participants today from their busy schedule, and look forward that they do some meaningful suggestions to our university for further taking this department to greater heights. And with these few words, you can continue with your deliberations and proceedings, and hope that once the pandemic is over and we as a university open up, I think more seminars where more student involvement is there, they are also needed, friends. And once we hold any seminar and students also participate, I think there is still more, great thing that we can do as a university and as a department. So thank you very much for inviting me, and you can proceed with your deliberations. My good wishes to all of you. Thank you.
Thank you, Professor Maitra, for this nice words. And now, before we start the lecture, I would like to introduce to all of you our esteemed speaker of today's evening, Professor Uday Maitra. He is currently Professor at Indian Institute of Science at Department of Organic Chemistry in Bangalore. He has completed his master degree from IIT Kanpur in 1981 and PhD from Columbia University, New York in 1986 with Professor Ronald Breslow. After a postdoctoral stay at the University of California, Berkeley from 1986 to 87, he joined IISc Bangalore and continued there since then. He is the recipient of Fellow of Indian Academy of Science 1998, Chemical Research Society of India Bronze Medal 2000, SS Bhatnagar Prize for Science and Technology, one of the highest Indian Science Award in 2001 for his contribution to chemical sciences. Professor T. Navneet Rao National Best Chemistry Teacher Award in 2005, J.C. Bose National Fellowship in 2008, Fellow of Indian National Science Academy in 2009, Silver Medal, Chemical Research Society of India in 2012, National Best Chemistry Teacher Award, JNCSR 2015, and Dr. Rastan Ramanathan Memorial Lecture, CRSI at IIT Kanpur in 2009, and many more. So he is also a member of various editorial advisory board and committees, like member of International Advisory Board, Chemical Society Review from Royal Society of Chemistry, editorial board member, Asian Journal of Organic Chemistry from Wiley, member of American Chemical Society, Royal Society of Chemistry, National Representative of IPSC Committee on Chemical Science Education. His research interests include the development of luminescent hydrogens, sensing of biomolecules, chemistry of and supramolecular chemistry of bioacid acids, design of molecular receptors, functional soft hybrid materials. He has published more than 150 research papers in various peer-reviewed journals with H-index of 41. He is actively involved in initiative for the popularization of chemistry in the country. So today he is going to deliver his talk on a simple, inexpensive and general photoluminescent sensor platform for multiple analytes. So with this few words, now I would like to invite Professor Maitra to start his lecture.
Thank you. Thank you very much, Professor Mishra, for the very generous introduction. I would also like to thank you and the department for inviting me to give the third Professor G.B. Behera Endowment Lecture. I'm truly honored to participate today, and thank you very much again. I didn't have the opportunity to meet Professor Behera in person, but I'm indeed very pleased to see you, Professor Behera, online. I have heard a great deal about you from one of your very illustrious students, Professor Bhishma Patel.
Bhishma Patel, BK Patel.
Yeah, Bhishma Patel. Yeah, momentarily the connection went off, so I just kept quiet. Professor Bhishma Patel of IIT Guwahati, and he was really in a lot of praise of you. And of course, we keep getting students from your department, including a very good student, Manoranjan Panda, who is a member of my group at the moment. So I thank you for really, building up a great department, which has produced many very able researchers, and also providing a steady supply of students, good PhD students, to many universities in the country. So with this, I would like to share my screen, and I will share my entire screen now. And for minimizing the bandwidth, I will simply switch off my video and go to my PowerPoint. I hope you can see my first slide.
Yes, sir.
Okay. Yeah, this is just to provide you with a number in case something goes wrong. Professor Mishra has my mobile number, but the mobile may not work in my office. So these are the two numbers in which I may be contacted in case there is any technical issue. So as Professor Mishra said, that I will be speaking on this subject today. And what I mean by multiple analytes are some of the molecules and species, macromolecules shown here. And you might see that this presents a very large variety of molecules and macromolecular species. But I will try to reorganize them into groups, and I will tell you how this project evolved. But before I formally begin, I would like to dedicate this talk to Professor G.B. Behera. Thank you again for this opportunity. So these are the molecules and macromolecular species and various small molecules which I had shown on the on my title slide. I should also mention that when we started this project about 10 years ago, it was not planned this way. It so happened that we were trying to explore a small, it was more of an exploratory project. And when we started, we had no clue that 10 years later, we will be developing a common platform for detecting a variety of molecule and molecular species by a common sensor image.
Sir,
So
sorry to interfere, sir.
Yeah.
Actually, you have to share it once again, because by mistake, Professor Behera has shared his screen.
Okay, no problem.
Okay, sir, sorry.
No problem. Thank you for the alert. Let me share my, I have to stop sharing and then resume sharing perhaps.
Yes, sir.
Yeah. Is it okay now?
Yes, sir. Perfect.
Excellent. Excuse me. So let me reorganize these molecules. And you will now see that they actually belong to 4 classes of species. On the top, you see a cup of green tea, which I'm sure some of you might be sipping right now, which is basically natural product extract. In the second row, I have a few medicines, naproxen, propanolol, norfloxacin, ofloxacin. In the third row, I have a variety of enzymes, typically hydrolases, lipase, glucosidase, lactase, this is beta-lactamase, alpha-glucosidase, and so on and so forth. And interestingly, in the last, and the fourth row, I have small molecules such as formaldehyde, hydrogen peroxide, and of course, a glass of water. So how can you develop a single platform which can detect most of these species with a common readout. So that's the story. As I said, I am going to tell you, and I will try to tell you the story as things evolved. Before I get to the real story, since our work involves a variety of gels or gel-like materials, let me give you, for the benefit of the students, particularly the master students and PhD students, a very brief introduction in 3 slides about gels and polymer gels. So most of you have experienced gels in various ways. For example, polymer gels have many applications in food, in cosmetics, medicine, and other fields. And these are some, commercial gelatin desserts. And most of the toothpaste these days, they come in the gel form. Many ointments also come in the gel form. Now, polymers, particularly carbohydrates, proteins, and nucleic acids, they all are known to form gels under certain conditions. But small molecule derived gels have received a lot of attention in the last 30 years. But this is not to say that small molecule gels did not exist earlier. In fact, the first report of a small molecule derived gel, in this particular case, uric acid or sodium urate, was published, this is not a typo, in 1841, where it was indicated that under certain conditions, this is in German, under certain conditions, you can get a gelatinous mass from uric acid. Now, that was 1841. And in the last 30 years, a lot of work has been done on small molecule derived gels, which incidentally, all of them aggregate and form almost polymer-like fibers. And these are typically sub-micro and in many cases nanofibers, which are produced through the aggregation of these small molecules. And my colleague Shantanu Bhattacharya, who in fact was an earlier speaker in the same series of lectures, and I had put together a chapter on molecular hydrogels in the first book on molecular gels, which was published in 2006. Okay, so let me go back and tell you how our story evolved. It turns out that almost 20 years ago, my former graduate student Samrat Mukhopadhyay, who is in IISER Mohali and doing extremely well, Samrat was writing a review on cholic acid or bile acids in chemistry and biology. At that time, he came across this particular publication, which said that upon reaction of sodium cholate, let me quickly show you what I mean by cholate. Cholate is basically a kind of a biosurfactant, which is a steroidal backbone, as I have shown here, and it has multiple hydroxyl groups and a side chain. So this is typically a class of molecules which are formed from cholesterol and are accumulated in the gallbladder in our fasting state, and they play a very important role in the digestion of fat and some other physiological applications. But that's a different story. So this paper, more than 100 years ago, reported that calcium salts plus cholate, sodium cholate, they form a gel. And at that time, the gel was described as a clot, as you see at the top of the screen. So we were curious about this. And when it was in fact done much later, around 2010, and when we mixed sodium cholate with calcium chloride, as reported by Shriver, indeed, it formed a very clear transparent gel. Now that was known, nothing new about it. But what we wanted to see is whether calcium can be replaced by other metal ions. As you know, the calcium plays a very important role in biology, but calcium is a relatively unreactive metal, like most other alkaline earth metals and alkaline metals. So we thought that if calcium can be replaced by other metal ion, which is reactive, such as a transition metal ion or trivalent lanthanide, then we can do some fun things with this gel. So this project really started in a completely exploratory manner without having an end goal. And that's how many sort of so-called blue sky research works, that you start with a curiosity question, and sometimes it can evolve into many important branches, and sometimes, of course, you reach a dead end, and then you have to stop. All right. So in our case, what happened is that when we mix this cholate with a variety of, in this particular case, first row transition metals and beyond, we found these beautiful gels from copper, cobalt, cadmium, zinc, silver, mercury, and this, as a reference, is the original one made by Shriver in 1914. So we have used we have done a lot of chemistry on these gels, particularly using the gel as a template for making nanoparticles, nanostructures, and so on and so forth. But I will not talk about those aspects today. Some of it was published during the second decade of this century. So that is between 2012 and 2018. We were also curious whether lanthanides would also form gels. And sure enough, when we treated colate, again, with all the available lanthanides, including praseodymium, you can see in these photos that they all led to the formation of semi-transparent and sometimes translucent gels, as you see here. Now, I'll show you the importance of lanthanides in a minute, but our focus was initially for examining these two lanthanides, europium and terbium, because they emit respectively in the red and green region of the spectrum. And they are used in a variety of devices, including something that you might be holding or looking at right now, and that is a smartphone. And if you look at the elements of a smartphone, the smartphone typically has something like 40 to 50 elements in it. And in the screen, you have a variety of lanthanides, including europium, praseodymium, and so on. And in the electronics, which also forms a very vital link in a smartphone, you have again dysprosium, praseodymium, and terbium. So today I will focus largely on europium and terbium. And these are the two lanthanides which are will be the focus of the rest of my presentation. So now that we know that these things form gels, my students put together a periodic table of metals which actually form gels with colate. I will very quickly show you to just illustrate some of these points, and for historical reasons, I have put these two names. Shriver, 1913, first reported the calcium gel, and Huang, another Chinese scientist, reported a lanthanum-derived gel in 2009, and some of these things just a few months prior to our publication. We were the first to report most of the other lanthanide gels, and this is what I would like to discuss today. So when we made these europium and terbium gels, and because these elements, these lanthanides, show photoluminescence, we thought that is there a way to make the gels photoluminescence? That is, you shine light and whether they will emit red or green color. Now we'll come back to what we can do with it a bit later. Now the problem with the lanthanides is that in the solid state they show good emission. They show phosphorescence, not fluorescence, because they emit from the triplet state. But in water, they do not show any luminescence at all because of low absorption coefficients. That is, their UV absorption is very less, and also the excited state is quenched by water. So the way people have handled this problem is by surrounding the lanthanide with a ligand. The ligand kind of replaces some of the water, and then what you do is that you attach the lanthanide with a spacer to an antenna. The antenna is typically an aromatic chromophore, so that since they are in close proximity, the antenna can absorb the light, transfer to the lanthanide, and then the lanthanide can emit. But for doing this, you need to have an appropriate ligand, a spacer, and an antenna connected. So basically, you have to do some synthetic work. But when we made these lanthanide gels, what we thought is that what I'm showing here is actually an electron micrograph of a gel in which you see these fibers that I mentioned earlier. Now, imagine that these green circles are the lanthanides in the gel, because we know that lanthanide and colate both are together in the fibers. And we also knew from earlier work that if I have a hydrophobic chromophore, say naphthalene, pyrene, anthracene, they do not stay in water because they're insoluble. So they go and stick to the fibers. Now, our sort of hypothesis was that if we now make a lanthanide gel and stick some chromophores, appropriate chromophores in the fiber, can there be a process similar to this, except that now the blue rectangle, which is the antenna, and the green lanthanide, which is this, they are not covalently connected. So there is no synthesis involved. You simply make a gel in the presence of a lanthanide, in the presence of an antenna. And if they are in close proximity, then you can virtually do this process and make the gel photoemissive. The big question was that, is it going to work? Very quickly we found out indeed that if I use dihydroxynaphthalene, this specific isomer, 2,3-dihydroxynaphthalene in the terbium collared gel, that made the gel photoluminescent. And this is a picture taken of this gel in the presence of dihydroxynaphthalene under a small UV lamp, which almost every organic chemist has in his or her laboratory to view TLC plates. Similarly, we found that in the presence of pyrene doped in the europium collared gel, we could make it photoluminescent and get a magenta color emission. I will not go into the details of why we are seeing red and why we are not seeing red and we are seeing magenta. But basically, these colors are visible only in the presence of this. There is also a matter of selectivity, because if I put dihydroxynaphthalene here or pyrene with terbium, there is no photoluminescence. So these chromophores are very selective for europium, pyrene, and dihydroxynaphthalene for terbium. So now the question is, what can you do with this photoluminescent gel? You know, it's one thing to show that, fun thing to show that it actually works. But then, why do we make these things? Okay, so in the next few slides, I will try to give you the basis for how we develop a variety of sensors for this. So the idea is that we used these photoluminescent gels for sensing enzymes, sensing small molecules, sensing drugs, and also developed a white light emitting system, but that falls more into the material side, so I will not discuss those aspects today. So let me try to give you a broad overview of the principles involved in some of the work that I'm going to describe in the remaining slides. So this is basically what I have explained in the earlier slides, that we have a lanthanide in a gel and we have a sensitizer that makes the gel photoluminescent. So the sensitizer are dihydroxynaphthalene, pyrene, or even hydroxypyrene. So the question was, are these only molecules that can make the lanthanides photoluminescent? Are there natural products? Are there drugs which have similar chromophoric behavior that can also make one or the other lanthanide photoluminescent? And that is something that I'm going to show you in some of the subsequent slides. The other way we thought we might be able to use this photoluminescence is that suppose something in the sensitizer that is causing this sensitization, suppose we block that by chemically modifying the sensitizer and make the gel photoluminescent. Can we then unblock it or unmask it to release the sensitizer, either, let's say, by a small molecule or by an enzyme? Depending upon how you have blocked it, you can trigger the unmasking process by small molecule, by enzymes, release the sensitizer, and that will make the gel photoluminescent. And that immediately tells you that by doing this particular trick, we might be able to detect these small molecules, detect these enzymes by this photoluminescence. The advantage here is that regardless of the nature of the small molecule or the enzymes, I'm always releasing the same sensitizer from the sort of masked sensitizer. Therefore, my detection is invariant of what I'm going to analyze. And I should also point out, again, without going into the details, that by this curvy line, I have indicated the gel, that these processes, this sensitization happens only in the gel. It does not happen in solution. Okay. Again, the reasons of it can be discussed during the discussion time. One more idea that is being explored by one of my students, it has been explored, but it is not published, so I will not discuss about it, is that just like lanthanides make these gels photoluminescent, there are many other metals which are not photoactive. So therefore, these gels are not photoluminescent. And therefore, we thought that if we now have a displacement, suppose we displace a non-photoluminescent metal by a lanthanide, and that will make the gel photoluminescent. And that immediately tells you that this will be a way to detect the lanthanide using its own photoluminescence by displacement assay. So I will not talk about it today. And this also happens only in the gel. And lastly, this is some work that was done by Manoranjan Sahu and another PhD student. That is, there are certain sensitizers that Manoranjan and Ajay Kumar found that they sensitize lanthanides in alcohol solution. So this is not gel. And then it turns out that while this alcoholic solution is photoluminescent, in the presence of water, it becomes non-photoluminescent. And therefore, that immediately suggested that if there is a small amount of water present in the alcohol, we might be able to detect it through the quenching of the photoluminescence. That is something I will talk about towards the end of my presentation. All right, so let's now try to look for natural products which can make the gel photoluminescent. Okay, it turns out that many natural products that you have heard about these days fall into the class of antioxidants. And these antioxidants are typically polyphenolic material. We were looking for polyphenolic materials because dihydroxynaphthalene is basically one of the members of a bisphenol, right? Bisphenol in the sense it has got two hydroxyl groups on an aromatic ring. It turns out that many of these natural materials, I won't say natural, you can say natural products, they contain antioxidants which belong to this gallic acid or derivatives category. So cloves, for example, lung, has gallic acid as one of the components. And very quickly, my student Tumpa found that the terbium gel can be made photoluminescent by doping with gallic acid. And that immediately provided a way for detecting gallic acid. And then it also turns out that green tea that I mentioned in the beginning, green tea contains many polyphenols, and some of them are not gallic acid, free gallic acid, but gallate esters. So we were also curious to know whether the green tea polyphenols will be able to sensitize, will be able to make these non-photoluminescent terbium cholate gels photoluminescent. So that's one of the things that we started a few years ago. And it turns out that the major polyphenol which is present in green tea is called EGCG. I will show you and I will describe you why it is named so. That has this gallate unit, and very quickly showed that not only gallic acid but the gallate esters also made these gels photoluminescent. So therefore, it was very easy for us to find out that how, for example, gallic acid and EGCG, the molecule I showed in the previous slide, they enhance the photoluminescence of terbium in the gel. So what I've shown here are actually the phosphorescent spectra of the terbium cholate gel. Terbium forms these 4 sharp bands, the most prominent one being the 545 nanometer green peak. And these are the actual spectra in the presence of increasing amounts of gallic acid and EGCG. And what we have done on this of the slide on the right hand side, on the panel on the right hand side, is to plot the intensity as a function of concentration. And this is a way by which you can find out the limit of detection by doing some mathematical manipulations. And we found that the limit of detection for gallic acid was 300 nanomolar, well below 1 micromolar, and for EGCG, well below 1 micromolar again, 360 nanometer. And what is shown here, interestingly, is basically a terbium cholate gel applied on a small filter paper disc. This is like a 5 millimeter filter paper disc on which you spread the gel, which shows a blue background fluorescence because of the filter paper itself. But as you keep adding more and more gallic acid, it adopts a green color, it changes to green emission. Same thing you see in the presence of EGCG. and we can selectively filter out the green radiation with a suitable detection system. So therefore, this process works. But these were done with purified gallic acid and purified EGCG. So would it work with raw tea extract? So here is also a control experiment that we did to understand the selectivity studies. We use other types of phenolic compounds such as dihydroxybenzoic acid, catechol, dopamine, fluoroglucinol, pyrogallol, and gallic acid. And it turns out, here I have plotted the intensity of the green emission line and these 7 molecular species. And you see that these first 6 did not show significant emission. Only gallic acid showed a very significant green enhancement of the luminescence, indicating that this is very selective. Having just 3 hydroxyl groups do not work. Now, coming back to these polyphenols, what are the major polyphenols found in tea? They basically belong to 2 classes of molecules. One is called catechin, which is a derivative of catechol and this particular aromatic ring, whereas epicatechin has this stereochemistry of the hydroxyl group inverted. So this is the cis, this is the trans isomer. And then you can either have catechin with 2 hydroxyl groups on the aromatic ring and gallocatechin with 3 hydroxyl groups. So just like you have gallocatechin, you also have epigallocatechin, which is the epimer of this particular hydroxyl group. So there are 4 of these molecules, and each of them can be now made into a gallet ester, and which is shown with the blue gallet derivative, and therefore you can have 4 different gallets. Now they are not present in tea extract in equal amounts. In green tea, typically this is a major component, followed by this, and this. So just to give you the numbers, 41% is this, 14% is this, and the other 3 are minor components. Now, only these 2 have gallets, and therefore only these 2 will make the gel photoluminescent. So we really do not care about this. So the question is, can a mixture of these 2 present in green tea be detected by our method? And indeed, in order to do that, we first did an HPLC of tea extracts. This is a standard HPLC of the authentic samples. This is gallic acid, catechin, caffeine. Of course, caffeine is present in black tea and green tea. And here you see EGCG and ECG, which is the minor component. Now, in white tea, I do not know how many of you have heard about white tea. White tea is actually it's made from the even fresh leaves of when the leaves come out of the plant, and it has got almost a white colorless tea you can get out of it, and that has the maximum amount of EGCG. And indeed, when this white tea extract was assayed by HPLC, you see caffeine, EGCG, and ECG. And similarly, green tea extract also shows EGCG and ECG. Black tea is a processed tea, and by the time you make black tea, all the polyphenols are gone. So you hardly see any EGCG or ECG. So this is consistent with what is already known in the literature. So what we did is to try now the raw tea extracts made under the same conditions and test their photoluminescence. Indeed, this is the blank. These are the 3 varieties of black tea from 3 different brands, 3 different brands of green tea, and a brand of white tea. And as you can see, that compared to the black tea and, excuse me, I need to cross this. Compared to the background, these 3 green tea samples showed significantly higher emission, and white tea showed even higher emission. And this was consistent with what we know. And it turns out that this green tea G1 was a sample of green tea that was lying around in my home kitchen for a very long time. And as you might expect, that with time, the amount of polyphenols will undergo decomposition because of oxidation process, and its content will come down. And we confirmed that this enhancement of luminescence is indeed because of the EGCG content by doing HPLC. Again, this is the standard HPLC. EGCG is shown in this purple sort of rectangle, and you can see that the black tea, B1, B2, B3, has very little EGCG, whereas the G1, G2, and G3 and W1, that is the white tea, they have substantial amount of green tea, as you see by the intensity of the peak between the lines on the right-hand side. It may not be very easily visible on your small screen, but this is how it is. But what I have done here is to essentially plot the intensity in black and the HPLC intensity of the EGCG peak, and you can see happily the two lines which are represented by the black, which is photoluminescence, and by blue, which is HPLC. They almost follow the same pattern, indicating that the fluorescence enhancement is most likely caused by the EGCG. We also did a check whether the intensity of emission coming from EGCG or ECG, this is ECG, this is EGCG, is affected by other polyphenols or other molecules found in the tea extract, such as caffeine, theophylline, this is catechin and epigallocatechin. These are polyphenols which do not have the Gallett unit. And we found that none of these things get affected. Independently, they do not sensitize the lanthanide. And we also found that the presence of these in the tea extract by indirectly mixing, for example, epicatechin with catechin, did not change the fluorescence emission. So I will not go into those details, but basically the sum and substance is that when we are able to detect this ECG and EGCG directly by photoluminescence, we can also detect the total amount of these two by photoluminescence of the tea extract. So the last thing that I'm going to talk to you about in this part is that I mentioned earlier that cloves contain gallic acid in the free form, and we showed that gallic acid indeed is present in clove extract, and that you can indicate, that you can detect by this photoluminescence method. Clove extract also has another aromatic component called eugenol, which actually gives the characteristic smell of cloves. This is the HPLC of eugenol, this is the HPLC of clove extract. You see a lot of eugenol, less amount of gallic acid, but eugenol does not affect the photoluminescence of gallic acid present in clove extract. So even clove extracts, amount of gallic acid can be detected by our method. So just to summarize this, I would like to also highlight that this paper-based sensing or the paper-based sensors that we develop, they are very inexpensive. We computed a cost of this, and it turns out that for each paper disc, this 5mm paper disc, the cost is about 13 paisa. And I just want to mention that most of the cost, in fact, is because of the lanthanide. Even the small amount of lanthanide, about 34 microgram of terbium acetate that we use, it actually costs about 10 paisa, okay, out of the 13. So, but nevertheless, since we use very little of it, with the presence of these polyphenols in tea can be detected rather easily in an inexpensive and straightforward manner. So the bottom line is that this is the sum and substance, that if you are drinking tea, but you are not sure whether you have black tea or green tea, of course, by the color you can detect, but sometimes with the old tea, you may not know. We have a very simple way of detecting the green tea. And also in some cases, we can quantify this, and the black tea does not change the photoluminescence of the paper disc. The green tea does, and it shows a green photoluminescence. Okay, so I described this part in detail. So the remaining part of detecting other types of molecules, I will discuss with 1 or 2 slides each. All right. So what about drugs? I said natural products such as EGCG can enhance the photoluminescence of the lanthanides. How about drugs? One of the things we were looking for are the drug molecules which have naphthalene or a more complex aromatic unit and some sort of a ligating group. Because remember, dihydroxynaphthalene, gallic acid or gallets, they have some sort of a coordinating group and hydroxyl groups on the molecule. So very quickly we found that there were couple of molecules which are in the market. Propranolol, which has a naphthalene and a ligating group of an amino alcohol. Naproxen, which has a naphthalene again and a carboxylic acid. Incidentally, propranolol is used for CNS active as a CNS active drug, central nervous system. Naproxen is used as a painkiller, similar to ibuprofen, for knee pain frequently. And there are non-naphthalene analogs of these, which are atenolol and ibuprofen, which you might be more familiar with. It's the component of the commercial name is Brufen. So we thought that if our idea is correct, only these two might enhance the photoluminescence of lanthanides, terbium, for example, but these two drugs will not. And sure enough, I will again summarize everything in one slide. We found that this terbium cholate hydrogel, which is otherwise non-emissive, can be made photoemissive in the presence of naproxen and propranolol. Both of them show very strong green photoluminescence, but the phenyl ring containing drugs, ibuprofen and atenolol, do not make it photoluminescence. So this is something that is selective, sensitive, and rapid. We can detect well below, very close to parts per billion presence of naproxen and propranolol. We can use, these are made from commercial ingredients. There's no background noise because we're measuring phosphorescence and not fluorescence. And we can use typical a real blood sample. There is no need for any processing. So, excuse me. So if somebody wants to detect the presence of naproxen or propranolol in a blood sample, it can be used directly. We have not tested in doing in vivo experiments, but we have taken a blood sample which we spiked with naproxen, spiked with propranolol, and we found that we have been able to detect these drugs in raw blood. Recent work which is being done by my student Ananya in the group also has shown that certain fluoroquinolone antibiotics can also be detected by this method, even when present as a mixture. But that's another story, and that is still unpublished. Okay, the other two points that I would like to highlight is the possibility when you can deliberately convert a sensitizer into a non-sensitizer by blocking some functional group here. And as I mentioned, this is a way to mask the sensitizer, make the gel non-photoluminescent. So we coined the term pro-sensitizer, just like people talk about drugs and pro-drugs. Pro-drug is a molecule which is not a drug, but converted to a drug in the body. So the question is, can we now have a non-photoluminescent gel with a pro-sensitizer where the unmasking can be triggered by enzymes? So to achieve this, what we did is to look for some of these enzymes, which I have shown in one of the earlier slides. And very simply, beta-glucosidase, for example, it hydrolyzes glycosidic linkages from glucose, in particular beta linkages. So what we did, we knew that dihydroxynaphthalene is a photosensitizer for the lanthanide. So we simply made the mono beta-glucoside of beta-glucosidase. Similarly, for the alpha-glucosidase, we made the alpha linkage, beta-galactosidase. Now, from glucose, which has the equatorial OH, we go to galactose with the axial OH, and so on and so forth. So we made these derivatives. For alkaline phosphatase, which cleaves a phosphate linkage, what we did is to take the pyrene, which is our hydroxypyrene, and simply put a phosphate group on it. Similarly, we made derivatives of lipase and lactamase, which I'm not showing today. So the question is, would some of these molecules not show photoluminescence? But because if they also show photoluminescence, then this project will not work. And fortunately for us, whenever we blocked one of the hydroxyl groups or this hydroxyl group, they were not sensitizing the lanthanides. So which is a good news. And then when we added the respective enzyme, it cleaved this particular bond or this bond, released the sensitizer, and the gel became photoluminescent. So here is an example with hydroxypyrene. The phosphate derivative did not sensitize the gel, but in the presence of the corresponding enzyme alkaline phosphatase, this group was cleaved, hydroxypyrene was generated, and the gel was made photoluminescent. So this is just to illustrate the process. And here is some quantification through photoluminescence experiments. So basically with the enzyme, this process works. If I don't add the enzyme, or if I kill the enzyme, that is denaturing of enzyme, then this process again does not happen, very clearly showing that this enhancement of photoluminescence is actually because of the presence of the enzyme. So we did a variety of enzyme kinetics to find out the kinetic parameters, to find out the limit of detection and so on, but I will not go into those details today. Here is also an example where we used this particular derivative. In fact, we used a propionate, not the acetate, and we showed that in blood serum and in saliva we have some lipases and non-specific esterases, and those can be detected in a broad way using this particular molecule. For example, in blood serum, there's a lot of these enzymes. In saliva, there is less, but these paper discs become photoluminescent with blood serum, and in saliva in as little as 10 minutes, and in 40 minutes you can see that really glowing. And the relative intensity gives you an idea about how much enzyme is present, and you can very quickly qualitatively say that saliva has less enzyme than the blood serum, which is along expected lines. Then for the beta glucosidase, we also showed that almonds, badam, also contain some of these glucosidases, glycosidases, and this can be detected by this process. This, for example, is a spot where raw almond extract, nothing more than that, was spotted on the paper, and you can see that it is glowing. This is without the extract, and in this particular case, I think this is without the extract. This is with the extract, but that has been heat treated to destroy the enzyme. On the right-hand side panel, I will not go into the details, but we also showed that you can study enzyme inhibition by this process. This was important to demonstrate because those who are involved in drug discovery project, they do a variety of inhibition studies. So we believe that our process, in an appropriate case, can provide a lot of inhibition studies to be done more efficiently. So this trick these gel-based assay can be used for assaying or for detecting or screening a large number of inhibitors at one time. So let me now go to the last part of my presentation. Professor Mishra, can I take another 5 to 7 minutes?
Yes, sir. Yes.
Thank you. So this is again a masked sensitizer, but here the triggering or the unmasking process is done by small molecules, not by enzymes. And let's see how this is done. I will show you one example, and the second example I will show only the summary. This is some work done by Deepankar and Arnab in my group, published last year, 2 years ago, in fact, in which what they found is that this biphenyl carboxylic acid can also make terbium photoluminescent. So what Deepankar and Arnab did was to mask this functionality with an homoallylic amine, because what happens in this homoallylic amine, in the presence of formaldehyde, it forms an iminiamine that undergoes a sigmatropic rearrangement and releases the aldehyde back, and that makes the gel photoluminescent. So this goes through an aza-cope rearrangement as shown here, but the bottom line is that this can be used for detecting formaldehyde in small quantities, and as this particular plot shows, that in the presence of increasing amounts of formaldehyde, these are units of micromolar, the intensity goes up. Maybe I should go to the other laser pointer. So you can see this is a control with no formaldehyde, and with increasing amounts of formaldehyde, the intensity goes up. And what we found is that the limit of detection is below 1 micromolar in this particular case. In fact, it turns out to be about 0.1 molar or 100 nanomolar compared to most other aldehyde formaldehyde detection system. Our system is actually simpler and more sensitive, or at least as sensitive as others which have been published. I will very quickly highlight another result which is in the pipeline, which is will appear in ACS sensors perhaps later this month. in which Arnav again developed a sensitizer for a sensor mechanism for hydrogen peroxide, again using a chemical means. This is using biphenyl carboxylic acid derivative. And what we showed is that you can detect hydrogen peroxide again in fairly small amounts. And you might have noticed that the hand sanitizers that I'm sure everybody is using during the last almost 2 years, some of them contain small amounts of hydrogen peroxide, 0.1 to 5%. Now, this hydrogen peroxide does not kill the COVID virus, but they kill or they destroy the fungal spores, which can sometimes be present along with the virus. And all of them, those which contain hydrogen peroxide, they all claim that as per WHO guidelines, they all have 0.1 to 5% hydrogen peroxide. So once Arnav developed this assay for hydrogen peroxide, we thought, let us buy 5 of these brands which contain hydrogen peroxide as per the label and find out whether by using our method, we can accurately find out the content of hydrogen peroxide. We thought that would be a sort of a COVID appropriate study since this was discovered, this process was developed during this time. Now, for brand names C, D, and E, I will not reveal which brands are these. As you can see, the concentration in millimolar and the concentration found by our method, they turned out to be very close to 0.1 to 5%. Okay, but there were 2 brands, A and B, which B, of course, had very little, 0.02%, which is 1/6 of what they claim to be here, and brand A had absolutely no hydrogen peroxide. So this was also a revelation because all these packages, they have some printouts which says that it contains A, B, C, D, E, which contains all these components. But sometimes if you do the analysis, you see that some major or key ingredient might be missing. So before I close, let me show you the last example, because this is also an example which was done by one of your very good students, Manoranjan Sahu, as I mentioned earlier. He's currently a 4th-year student in my group, and he did this work in collaboration with Ajay Kumar, and this is for the detection of water in alcohol. And as I mentioned earlier, that in the presence of certain sensitizers, in particular salicylic acid, terbium can actually be sensitized in alcoholic solution, pure alcohol. It can sensitize and make it photoluminescent. So the idea was that now if I add controlled amounts of water, small amounts of water to the alcohol, will it make the gels non-photoluminescent? Will it quench the luminescence? And can we detect the presence of water, or can we quantify the water content in the alcohol by this process? It turns out that this was indeed possible. So we published a paper in AJOC last year. And here again, I show the result initially that this terbium and salicylic acid in water, it shows no luminescence, which is shown in the green line, the red line. But in the presence of salicylic acid in methanol, the luminescence significantly increases. So this is pure methanol, this is pure water, and now we are going to take the methanol solution and add small amounts of water. And what happens is when you add small amounts of water from this is 0 to about 2%, you see a substantial decrease in the intensity of this particular peak. So what we did is that we processed this data and plotted it versus the concentration. We also used not only methanol, but ethanol, THF, and acetonitrile. And what we showed is that in each case, if I plot I0 by I0 is the intensity in the absence of water, I is the intensity in the presence of water. If I plot it at least up to 4% of water, it showed a linear plot. The slopes are different depending upon whether we have methanol, ethanol, acetonitrile, or THF. But in all these cases, we can detect, between 0.5 to about 3 or 4% of water just by doing 2 measurements of in the presence of salicylic acid and terbium. All it requires is the availability of the pure solvent, which has been substantially dried. And this is a much easier method compared to, for example, the Carl Fisher titration, which people do for detecting small amounts of water. Of course, we cannot go beyond 0.5%, so that's the limitation, but between 0.5 and 4%, it can be very easily detected. So that is the end of my story. But before I do that, I would like, before I conclude, I would also like to show you one particular development that is taking place. It has not reached a concluding situation yet, because I showed that, you know, we can detect these images simply by putting it under a UV lamp. Now, these can also be quantified using a appropriate software. So what it requires is that prepare a sample, photograph under UV lamp, transfer to a computer, and then use an image processing software to measure the intensity. So the question was, can we combine steps 2, 3, and 4 using a small device? This is something we are trying to develop through collaboration with a company making medical instruments. So we now have a prototype which looks like this, where we can insert the paper discs through this sample, and here's a touch screen which allows us to fire LEDs of our choice, and with any time delay. So it's sort of like a small miniature fluorescence spectrometer or phosphorescence spectrometer by which we can detect the photoluminescence, measure the intensity. We still have some teething problems with the instrument, but we hope that in the future we might be able to use a device such as this for very rapidly detecting various types of analytes. So that's really the end of my story. And as I mentioned to you earlier, that when we started this project almost 10 years ago, we had no clue that 10 years later we might be able to develop the system into a situation where all these molecules and macromolecules shown we will be able to detect them by using a single common platform. And as I showed earlier, we can detect the polyphenols in natural products, several types of drugs, several types of enzymes, and many small molecules. So our future work will involve expanding the list here, expanding the list in all these cases, and make things which can be practical and easy to detect. So with this, I would like to conclude. But before I do so, let me thank who are the players. You know, they actually do all the hard work. I only come and put things together and present. So this was my group about a year or so ago. Since then, Ajay had left, Shruti has left, and this is Manoranjan, who is a student of your alumnus of your department. So I thank all of them for doing all the work that I have put together and presented today. I also thank the financial support from SERB and IISC. And finally, thank you all very much for giving me a chance to spend the afternoon with you and share some of our interesting results. Thank you very much.
Thank you, Professor Maitra, for illuminating us interesting talks on photoluminescent materials, gelation, sensors, and using multiple analytes and so on. I hope there will be some interactions with our SARs and other members sitting in the Google Meet platform. Yes, sir.
What is the stability of the gels, pH stability? Because they have all hydroxy groups are there, your phenolic weights are there. pH stability.
Yeah, these gels are pretty stable because as prepared, we don't use any buffer because the sodium cholate itself acts as a buffer. And these typically have a pH, in fact, very close to the physiological pH of about 7.3. What happens at lower pH? We have examined these photoluminescent properties as a function of pH, because depending upon which lanthanide salt you use, whether you use nitrate, chloride, or acetate, the local pH can change. So we've examined these, and what happens if you go to a very low pH, the cholic acid starts to precipitate. If you go to a higher pH, some of the oxides and hydroxy oxides of the lanthanide starts to precipitate. So they have a small window, but it happens to fall in the physiological pH range. So we don't do anything special.
Yeah, by that one can mask and demask the sensor also
In
by changing
principle-
pH little bit.
In principle, yes. The only thing is that, you know, sometimes if we go to a lower pH, the cholic acid will precipitate, and it may not be easy to again go back because we are in the gel. We are on a paper platform, so it may not resolubilize to regain the gel property, because we are not doing some all assays in the gels. We are doing it in the dried form of the gel on the paper. So that's an important question.
Sir, the stability of the gel,
Yes.
the formation of gel or this, that depends on the water content, right? That also would mind.
We make the gels under very specified conditions. For example, we use about 5 millimolar lanthanide, 15 millimolar cholate. We maintain the stoichiometry as 1:3. And that seems to have fairly, I mean, you can make the gel in a sealed tube and it will stay forever. Well, for several months.
Okay. So if they come in contact with organic solvents, there is no problem like in the dehydration or
No,
something?
in fact, there is. In fact, sometimes we break the gel by adding THF. If we have
Yeah,
to break
yeah,
the
that
gel,
is what.
in the presence of THF, it destroys the gel. So you cannot keep it in the presence of an organic solvent. But what we
Yes.
can do is that, you know, when I make the gel from, let's say, terbium chloride and sodium cholate, so a byproduct will be sodium chloride. We can actually make the
Yes.
gel. We can actually put the gel in a small column and pass water through it. The gel more or less remains the same, but all the sodium chloride, which is in solution, it comes out, leaving behind the terbium and the cholate in the gel. There's a little bit of shrinkage, but, you know, that is because of perhaps hydrostatics and not because of any sort of other mechanism for shrinkage of the gel.
So generally the cholates, like the trihydroxy ones, generally don't form gel so easily as compared to the dihydroxy one. Have you observed something like that?
You are right. I mean, in terms of sodium cholate and sodium 7-deoxycholate, in the absence of a metal ion, there are more literature reports on the formation of gels. In fact, in the late 1950s, a Czechoslovakian group first published the formation of gels from sodium deoxycholate.
Change of pH.
Yeah. By changing the pH within a small window.
Yes, sir.
From 7.5, you titrate to about 6.5 and you get a
6 point, yes.
It also happens with sodium
Higher concentration, I think.
cholate at a higher pH. Cholic
Yes.
acid is not from a gel, alone. But in the presence of a metal, the situation changes. Although we have been able to make sodium deoxycholate gels of cadmium, for example, and a few other metal ions.
Yes, sir. Thank you, sir.
Thank you all. So when there is no more questions, thank you, Professor Maitra, for illuminating us with this many interesting aspects of chemical science, and thank you for joining us and accepting our invitation.
Thank you.
And hope sometime later, when it is over, we can invite you over here to Sambalpur University.
Surely. And then once again, my regards to Professor G.B. Behera. And also I would like to say hello to Professor Maulik and Professor Mandal, whom I see in the audience.
Yes, sir.
And Professor Anandi Das. Namaskar.
Sir. Sir,
thank you very much.
Yes, sir.
Thank you.
Sir, on behalf of School of Chemistry, we are now giving you, we send you this very token of appreciation. We have this medal, the memento, a certificate, and a shawl. We'll send you by post.
Sure.
And we also give you 5,000 rupees, which will send you to your account. I'll write you an email later on. And thank you again.
Thank you.
Das.
say no.
Thank you very much.
Thank you.
Bye-bye.
Thanks, Dilip. Dilip Chand is also there. Thank you, Dilip. And thank you all attending this.
Yeah.
Okay, Dilip,
Thank you
also
very
your
much.
alumnus.
Okay.
Thank you very much. Professor Maitra, thank you very much.
Thank you.
Long after
Bye-bye.
we are meeting.
Okay.
Long after. So nice to see you. See your smiling face.
Professor Maulik is also there.
I think Dr. Maulik is also there.
So, Professor Maulik, namaste. So, all,
Where is Professor
thank you very
Maulik?
much.
I think unmute your mic.
Dilip, thank you.
So unmute, Professor Maulik, unmute your mic. I think it is muted.
Professor Maulik, your mic is muted.
Unmute it, please. Professor Maulik, please unmute.
Yes. Now you can hear me?
Yes, sir.
Hello?
Yeah, we can hear you.
Yeah, so I can see Professor Behera, Professor Anari Das, and Professor Maitra and Professor Mr. Roll. And your next classroom, lecture theater, I can see where we used to meet many occasions. So nice meeting all of you. It's a very good occasion. And Professor Maitra, I heard you say a nice new lecture. So most of things I cannot understand, clearly. It takes time. Anyway, so thank you all. Okay, see you again sometime.
Okay, sir. Thank you.
Okay.
Thank you very much. Thank you very much.
This is the end of session. Yes, sir.
Okay.
Okay.
Have a nice evening, all of you.
Yes, sir. I'm End of the call.